All right, another question I have had questions on is this related rates problem. And so I wanted to look at this with you. The top of a 15-foot ladder rests against a vertical wall with the bottom of the ladder on level ground as shown. The ladder is sliding down the wall at a constant rate. So remember, anytime you see that phrase, a rate of, we want to think derivatives. And so it's sliding down the wall at a constant rate of 2 feet per second. At what rate? Again, there's that word rate, and which indicates that's what we're trying to solve for as a derivative. At what rate in radians per second is the acute angle between the bottom of the ladder and the ground changing at the instant the bottom of the ladder is 9 feet from the wall of the base? The base of the wall. Okay, well, we've got a lot going on here, so let's go ahead and define some variables. One, it's a 15-foot ladder, so the ladder is 15 feet this way. Maybe we call this side B, and we call this angle theta. Okay, so there's a couple thoughts. I know I'm trying to find d theta dt, because that's the angle that's changing, the rate at which the angle is changing. So I'm finding d theta dt when b equals 9. Okay, but we also know dA dt is a negative 2 feet per second. So it's sliding down the wall. So now I need to try to relate all these things, thus the name related rates. And your first thought might be, okay, well, I see that I'm going down, A is moving, B is what I'm trying to find. So your first thought might be to try tangent. And if we look at tangent of theta equals A over B, the problem is if I take the derivative of this right now, I'm going to have a theta, a d theta dt, an a dA dt, a b and dB dt. And the problem is I don't know how b is changing. I know it is changing, it's the base is moving, but all I know is I'm trying to figure out this value at the moment b is 9. I know nothing about how it's changing. So this is not a great formula to use for this one. So now I'm going to go back to the idea of this 15. Why did they give me this piece of information? Why did they tell me the ladder was 15 feet? It does matter. And so what I'm going to do is I'm going to relate that 15 to the other thing that I know is changing. And let's use the sine of theta equals A over the hypotenuse, which is 15. 15 is not changing. It can't change while it slides down the wall. So now what I'm going to do is I'm going to take the derivative of both, or of this equation with respect to time. And the derivative of sine is cosine theta, but I took the derivative of theta with respect to time. And the derivative of A over 15 is actually just 1/15th, but I took the derivative of A with respect to time. Okay, well, I've got some good news. This quantity right here, this dA dt, we happen to know. We know dA dt is this negative 2 feet per second. We know what I'm trying to find, ultimately that I'm trying to find, is this d theta dt, that's there. Okay, so what about this cosine of theta? Okay, do I know theta? No, I don't. And this is on the non-calculator section, so it's not like I could do an inverse to figure out the angle theta. But I am going to use the idea of trig ratios. And remember, we had this other piece of information that said when b was 9. Well, here's what I know. At the moment b is 9, we know that the cosine of theta has to be 9 over 15. At the very moment that that ladder is 9 feet away, the cosine of theta is 9 over 15. Well, I don't need to replace just the angle of cosine. I can replace the entirety of cosine with that 9 over 15. So then I get 9/15 d theta dt equals 1/15th times negative 2. And so then we can solve it and get 9/15 d theta dt equals negative 2/15. I would multiply by 15 and we get d theta dt. The angle is changing at negative 2 over 9. It's in radians, so radians per second were the units. I would always put your unit on a related rate problem at the end. And there's problem 28.